We're going to continue talking about techniques of integration. This next technique is a big important technique for us. It is part of Calc 2, so it only shows up on the BC exam. It's called the product rule for integrals, and we'll see why it's called that, but we call it integration by parts. We find the different parts that are involved, and then we can find the antiderivative of those different parts. So let's do a review. Remember, the product rule for derivatives says that if I'm taking the derivative of the product of two functions, here I have function f times function g. Well, we learned it as 1 d2 plus 2 d1. That's how we learned our product rule. And that was if given the product of function 1 times function 2, then we wrote function 1 as it was given to us times the derivative of function 2, and then we copied a plus sign down, and then function 2 as it was given to us times the derivative of function 1. So we recognize that to be our product rule for derivatives, and we've used that enough, we don't have an issue with that at all. So wouldn't it be true that if we integrated both sides of this equation with respect to x, then these two operations are inverse operations. They're going to undo each other, and they're going to map us back in math speak. They're going to map us back to where we started. And what we're going to wind up with over here is the integral of f of x times g prime of x with respect to x plus the integral of g of x times the derivative of f, or f prime, with respect to x. So this is a true statement. If this is equal, then this result must be equal. And so we're going to use this solution to actually generate the, I guess, formula, probably is what we should call it, for integration by parts. But I want you to see that it clearly comes from what we already know about the product rule for derivatives. So here it is at the top of this slide, and this is what we had. It's kind of flipped on either side of the equal sign there. But the integral on the left must equal the product of f and g. Now I want to introduce some different notation, maybe to make this a little bit easier so we can see it. You usually see integration by parts given to you in terms of u and v. So let's call our function f, let's call it u. So up here, anytime that we see f, we're going to write u. So those are the only two times that I see f. And let's call function g v. So up here, anytime that I see g, I'm going to write v. So do you agree with that? All right, so if we're going to call u f of x, then du should be f prime of x dx. Remember, the derivative can be written as the differential by multiplying through by the differential on bottom. This is stuff we already know. I'm just kind of giving you a reminder. So anytime I see f prime of x dx, I can just write du instead. So there we go. There's f prime of x dx. I'm calling that du. And in the same vein, if v is g of x, then dv should be g prime of x dx. So when I see g prime of x and the dx is over here, it distributes and applies to both of them, I'm going to call that dv. So I have two integrals here. I have the integral of u times dv plus the integral of v times du, and that has to equal u times v. So hopefully you see that right here. That's where this came from. And this is usually the beginning of integration by parts. So it has to be true that if I have two unique functions, u and v, and let's say I had an integral that was one function u times the derivative of a completely different unique function. I have two functions that are completely unrelated. U has nothing to do with dv inside that integral. And over here I have another two functions that are completely unrelated to one another. V has nothing to do with du. That's representing this portion of that integral. And remember, integrals do break up over the plus sign. So integration by parts says use some algebra on this and solve this for one of your integrals. We usually solve it for that integral right there. And that's how we wind up here algebraically. And I'm going to put this back in terms of f and g so you can kind of see what we're talking about here. This is how you're normally going to see that in your textbook and things. They use this notation so you don't get all bogged down in the f's and f's primes and g's and g primes. But it's the same thing. If we called u function f, this is saying if I have f times the derivative of another function that has no relationship with f, I have f times, we'll call that the derivative of g, that has to equal f of x times g of x minus the integral of g of x times f prime of x. Now, all of that followed from our product rule for derivatives. Hopefully you see that's where that comes from. So this allows us to actually find a way to integrate an integral to find the antiderivative when we have the product of two completely unrelated functions. And we do this with integration by parts because remember, integrals do not break up over multiplication. So integration by parts, there is the indefinite integral, and the same is true for the definite integral. If we have the product of two functions and it's not a u substitution and it's not something that we can do any kind of algebraic or trig substitution in, then we can attempt to use the technique of integration by parts. That's what this is saying. Okay, whether it is a definite integral and we use fundamental theorem, or whether it is an indefinite integral and we just find the antiderivative function. Now, it is true that we're still going to have an integral in that result, and we hope, it is our hope, that this integral is simple enough that we can go ahead and evaluate it and find the antiderivative. Sometimes what happens for us is we may have to do integration by parts. Again, we can do multiple steps of integration by parts if it's necessary. Now, there's one more thing we need to talk about for integration by parts, and that is how we find all of those pieces. Now, we're going to start out with two functions. We're going to call one of those functions f of x. We're going to call the other function the derivative of some other function g. And remember, this was u dv. So we're going to have to choose. We have four players here that we have to find in order to plug them into this formula. And the four players are, we've got to find f of x, so we can take the derivative of it. That'll give us f prime of x. We do, if we're given f of x and we choose one of the functions that's in our integral to be f of x, the other function that's in there by default has to be g prime. And so we'll need to integrate that, and we'll need to find g, because the very first part of our formula is f times g. So now let's drop f's and g's, and let's just stick with u's, v's, and du's and dv's. So we're going to choose u. This is how we're going to do this. We're going to be given, here's an example, we're going to be given an integral that is the product of two functions that really don't have anything to do with each other. This seems like a simple, straightforward integral, but if you'll notice, we've never been asked to integrate that before, at least not without a calculator, because we don't know how. This is the product of two functions. It's not a u substitution. Integrals don't break up over multiplication. We don't know how to find the antiderivative. If it was a definite integral, we could do it on our calculator, but this isn't even a definite integral. This is an indefinite integral. So we need four players. We need u, and we can find du. Once we choose what u is, what's left by default has to be dv, and then we'll integrate dv and we'll find v. So there are the 4 players that we need to even be able to do integration by parts. So there's a loose guideline, notice the word loose, it's not hard and fast, on how we choose u. Because once we choose u, everything that's left over has to be dv. And that is LIPET. So make sure that you put LIPET in your notes. Make sure you understand what the L, the I, the P, the E, and the T actually stand for. This is the order in which you're going to choose this type of function to be u. Let's say you had an integral that was the natural log of x times the sine inverse of x, dx. Well, LIPET would tell you to choose u as your logarithmic function, and since inverse trig shows up in LIPET after logs, it would be forced to be dv. Let's say you had the natural log of x times e to the x. Well, again, LIPET would tell you, since L comes before e in LIPET, that u would need to be natural log of x, and e to the x dx would have to be dv. But let's say that you had the sine of x times e to the x dx. Now LIPET tells you, since e comes before t, this is an exponential function, here's a trig function, that e to the x needs to be u, and sine x dx would have to be dv. So there's the idea behind LIPET. LIPET tells you the order in which you should choose a function that's present to be u, and therefore everything that's left by default has to be dv. So let's do this example using LIPET. We have a polynomial, x is a polynomial, and cosine of x is a trig. So according to LIPET, u needs to be our polynomial, and everything else by default has to be dv. Because remember, we're dealing with u dv equals u times v minus the integral of v du. So if we know what u is, we can find du by differentiating it with respect to x. Well, that's just 1 dx, right? And if we know what dv is, we can integrate it with respect to x, and we can find what v is. So what did I take the derivative of to get positive cosine of x? That was positive sine of x. So finding those 4 players is usually not that difficult. It can get complicated, and it becomes really important that you make good choices for u. All right, so we're going to plug the integral of x times cosine x dx into our formula. And that says that it has to be u, which is x, times v, which we said was sine of x, minus the integral of v, which again is the sine of x, times du, which is simply dx. And sure enough, here we have an integral that's very simple, and we can evaluate that. So this is x times the sine of x minus, be careful here, make sure you put a minus down in either a parentheses or a bracket, because if you have to do integration by parts again, your complete result after this minus sign is going to be affected by that minus. So be really careful with that. So what did I take the derivative of to get positive sign for the answer? That was negative cosine. And then this is an indefinite integral, so I need to make sure I put my plus c. So quickly, the antiderivative on this first example is x times the sine of x plus the cosine of x plus c. All right, so look for the next video. We're going to work some more examples of integration by parts.